Hello everyone, Project Gladiator here. In this video, we will be straying away from our usual daily forecast, and we will be looking at something a little bit different. As the title suggests, we are going to be looking at how to read different various radar products. The radar products that I will be going into today will be reflectivity, velocity, and correlation coefficiency, so you guys can get an idea of what all these radar products mean whenever I'm looking at them on my live streams for significant weather. And if you are going to get into any field of meteorology, it is very, very good to know how to read radar. It is a very important thing to know how to read radar if you are going to be doing anything with meteorology. So first off, we will be taking a look at reflectivity radar, and the day that I currently have us set at is June 14th of 2023. So on this day, there was a moderate threat for the Dixie Alley region, and there was a 10% tornado threat with the possibility of strong to violent tornadoes on this day as well. And many of these storms that you see right here were tornadic as well. So you might be able to see a little bit of stuff over here. This is a severe thunderstorm watch with a severe thunderstorm warning and a few special weather statements there. Do not worry about that. That is for today. I can't really get rid of those for today's video, so just ignore them for now. But I will be looking at reflectivity for the time being. So what reflectivity essentially is the radar site sends out a beam, and it measures how much of that beam is being sent back to it. So the higher that beam is being reflected back to the radar site, the higher reflectivity values you are going to have. And what might be associated with higher reflectivity values could be hail or even heavy rain. So you can see a lot of these supercells here. You can see a very well-defined supercell right here with the hook echo, and a well-defined supercell here as well. You can see right here there is some very light purples. That is going to be some large hail. But then let's focus on our hook echoes and how you might be able to read them and associate them with tornadic development. If we roll it back and take a look at some of the more notable supercells that did occur on these days, you can see that there are three supercells very close by that are very, very prominent here. We have one supercell up top, one supercell in the middle, and one supercell further down south. I think all of these did produce at least a little bit of tornadic genesis, and I know that the southern one did produce a tornado. Reed Timmer did see that tornado, and I did post it in our Project Gladiator Discord server when this day did occur. If you want to check that out, you could probably also find it on his Twitter. What we're essentially looking for in terms of hook echoes for tornadic development is these little hooks that develop off of these supercells here. You can see it is a very tight region of lower reflectivity off of the main storm core. You can see on the more defined supercell here further down south that did produce a tornado. The main supercell core, the hail core here, there is some hail in that as well with higher reflectivity, and you can see an area of lower reflectivity in the yellows and the oranges and the greens. That is going to be your hook echo, and it is much tighter than the main storm core. Main storm core does look like a blob mostly. You see it does get tighter compared to the rest of the storm core. Main storm core does look like a blob, and then it does transition into a very tight region of lower reflectivity. And at the very end of that hook echo here, that is going to be your area of tornado. That is going to be where your tornado is, and you can tell that it is a hook echo because it does have some higher reflectivity and higher reflectivity with an inflow notch in between it and the hook echo extending off the storm. We do have an inflow notch on this hook echo as well. Most hook echoes do have an inflow notch. This is a very, very textbook hook echo here, so I can find an even more textbook hook echo if we do go to April 19th, I think. Alright, so about the textbook hook echo, I am not able to show that as Radar Omega is giving me issues, so I am going to stick with the June 14th event. And I will try my best to show you guys the different radar models. However, it's a shame that I can't get the April 19th supercell to load, as that is a very textbook event and would help immensely with this video. So now let's switch to velocity here. So what velocity radar is take this radar site right here, okay, in southern Alabama. All the greens and blues are going towards the radar site, while all the reds are going away from the radar site. and the stronger the blues or greens may be, the stronger the wind speeds are as well. And you can see right here as well, we have very, very strong wind speeds as far away from the radar site as we can tell. We do have wind speeds from that radar site in this storm area that is reaching 90 miles per hour and even 100 miles per hour in some areas. So this is going to be very, very strong winds. However, this is not tornadic. This is going to be damaging straight line winds, or destructive straight line winds, I should say. Very, very strong winds that are in a large area that aren't associated with any hook echo or anything are going to be damaging straight line winds and not associated with tornadic genesis. But then let's take a look at some of the supercells that we saw on this day as well. The 3 supercells that I am going to be mostly focusing on. This was a highly sheared environment on this day. As you can tell, we did have a 10% tornado threat with the possibility of strong to violent tornadoes and expected weak tornadoes. Let's focus on one of the supercells. So you can see the radar site off to the left here. You can see focusing on the southern supercell where that very defined hook echo was. Again, this did produce a tornado. So greens are going towards the radar site and reds are going away from the radar site. This is very textbook rotation on this particular supercell, and this would definitely be sufficient for strong tornadic genesis. And again, this did produce a strong tornado in this region. And some other examples may be the supercell that was further up north. It is weaker rotation, but you can definitely tell it is some rotation. You don't really necessarily have to have greens if everything is moving away from the radar site. You don't necessarily have to have greens going towards the radar site in a counterclockwise rotation for tornadic development, as it can also be as if it's moving away from the radar site fast enough, then it can be close to 0 miles per hour while stronger reds are going away from the radar site. So this would definitely be rotation here as well. And what we call areas rotation associated with tornadic development, we call these velocity couplets. Greens next to reds in a counterclockwise motion towards and away from the radar side in an area of rotation is called a velocity couplet. So now let's take a look at correlation coefficiency. I know a lot of people were confused on a Chicago severe weather event live stream with the possibility of violent tornadoes in the Chicago metro region. And people, again, were very confused about correlation coefficiency, so I thought I would cover it in today's video. Again, the 3 main radar products that we are going to be covering are going to be reflectivity, velocity, and correlation coefficiency. So this is going to be the last radar product until the end of the video. So let's go out into the ocean here so I can draw you a little model of what correlation coefficiency really is. Correlation coefficiency is the measure of how much items or objects in the atmosphere correlate to one another in size. So take our radar site right here. This is going to be our radar site. I know it's a very, very crude drawing of a radar site, but say you have a storm right here, and it is dropping a bunch of rain. Rain is typically the same size, close to one another, so that is going to give us a high correlation coefficiency being detected by that radar beam, because all the sizes of every rain particle usually correlate to one another and are very similar in size to one another. But say we have a tornado on the ground that is doing damage on the ground and lofting debris. A lot of these different objects are being lofted into the atmosphere by this tornado, like sheet metal and then screws. Those sizes differentiate a ton from each other. So say you have like huge pieces of sheet metal and you have like tiny screws everywhere and different pieces of wood and plywood and stuff. That is going to pick up on the radar site as a very low correlation coefficiency. So you can tell if a tornado is on the ground if there is a correlation coefficiency drop right where a velocity couplet is. And that's, again, a very surefire way of telling if there is a tornado currently on the ground. So then let's go to one of these tornadoes here. The one tornado that I did say was doing damage and destruction to something on this day there was a correlation coefficient drop associated with this supercell, because again there was a tornado on the ground that did do damage. So this right here is our target supercell that we have been focusing on for the most part for a lot of this video. You can see right here where the hook echo is. You can kind of see it on correlation coefficient with the big blob of the core here. You see there is a little bit of low correlation coefficient, more so in the medium drop. That is going to be associated with rain and then also hail. Those sizes are going to differentiate, so that is going to lead to a slightly lower correlation coefficient compared to all the reds that are around it. But you can tell if it's being contaminated by hail if it is in a hail core. But if you have a very, very low correlation coefficient on the very end of a hook echo, like right here, a very low correlation coefficient right next to a very high correlation coefficient on this hook echo, that is going to be associated with tornadic debris in the atmosphere. And again, that is a very surefire way of telling if there is a tornado on the ground. So if we piece all three radar products together, forget about this second reflectivity panel down here, but you have the velocity, reflectivity, and correlation coefficient down here. So I will label them CC, correlation coefficient, V for velocity, and R for reflectivity, just if you're not really confident about what radar products are which. You can see with this same supercell, we have the hook echo with our supercell right here, our main storm cores right here, and we have our inflow notch, and a little bit of a debris ball as well. That is going to be where our tornado is. And then you can also see where the radar site is further off to the west somewhere. We have greens that are going towards the radar site and reds that are going away. That is going to be your velocity couplet on radar. And then as for correlation coefficient, you can't really see it all too well on this current scan. However, there is a little bit of a correlation coefficient drop at the very end of that hook echo with the faint hook echo right here. So that is going to be maybe dust from or leaves or branches being lofted into the atmosphere by the tornado. It's kind of hard to tell. It's maybe not hitting like any infrastructure at this point, as there's probably not screws compared to sheet metal in the atmosphere. It's probably more so branches compared to pieces of dust and leaves. So it is going to have a higher correlation coefficient, but still a notable correlation coefficient drop without hitting any infrastructure. But then if we do go to a scan where we have a very notable correlation coefficient drop, you see on velocity it is contaminated just a little bit, but you can still tell that there is rotation in there. But then on reflectivity we still have the hook echo and what looks to be a little bit of a debris ball and even a little bit of a RF detail on the back of that. And then as for correlation coefficient, you can see that we do have that very strong correlation coefficient drop. So right now on this current scan, this could be hitting infrastructure and being and the radar site is probably comparing sheet metal to nails and screws in the atmosphere. So there's going to be a much lower correlation coefficient compared to a few scans back when there was still a low correlation coefficient, but it was much higher compared to this. So this is what you're mainly looking for when you're looking for tornadoes on your radar. And then before I end today's video, I do want to touch on our ongoing severe weather for today. If we go to velocity here, you can see some fairly strong winds ahead of those storms. On the very front of those storms, you can tell that it is moving away from the radar site because it is in the reds, and all the greens are again going towards the radar site and all the reds are going away from the radar site. And you can tell the direction of where it is going based on the line of 0 miles per hour where it transitions from green to red. So you can see that the winds are moving in a westerly fashion over to the east, and you see towards the front of that storm system there, we are expected to see some fairly strong winds that are getting up to the 50 miles per hour and 60 miles per hour across this area here. And if we go back to reflectivity, you can tell where higher areas of winds might be, as we have the main storm system here, and then also another main storm system here. And you see a little bit of a bowing segment out. That is going to be associated with higher winds pushing the storm further out compared to the rest of the storm. So that's going to be associated with much higher winds with that bowing segment, and you can also see there is also a little bit of hail associated with this system as well, with some purples and deep reds. So that's how you tell where high winds might be if you don't have access to velocity radar. However, a lot of times you'll probably just check velocity radar and see that there's much stronger winds in that region. But then you might be noticing this line here that is separate from the rest of the storm. This is what we call an outflow boundary. So what an outflow boundary is a boundary of strong winds that is moving out of the storm system. If you see an outflow boundary, it could allow for the possibility of some storms that could develop along the outflow boundary. As you do know that I do say storms triggered by outflow boundaries or aided by outflow boundaries in my daily forecast a lot of times. If there's overall weak mid-level flow aloft, sometimes it will be aided by outflow boundaries if there were strong storms in the area just the day prior. So this is what an outflow boundary is, and if you see an outflow boundary, it could mean that the storm could be dying slowly as it is becoming mostly outflow dominant and may not be able to keep itself going for much longer. More so in this region where the outflow boundary is, you can see it is beginning to fall apart, but where you don't have the outflow boundary is the area of stronger reflectivity and much more in higher organization. So this area is going to continue going, but this area is beginning to fall apart. I hope that this helped with understanding radar better, and if you are looking at getting into anything related to meteorology, I do suggest learning how to read radar first, and that's what I did before I got into any in-depth meteorology details with like pivotal weather models and all that. I started from the basics and I started learning radar. So if you're looking at doing anything with meteorology, learning how to read radar is a very basic thing that you have to know, and I suggest learning it before you learn anything else. So again, I hope that this helped, and hopefully I will be able to see you guys tomorrow with a daily forecast.